So really have the pleasure of having, and you've heard that optics and laser experience is actually quite sought after in the quantum industries. So we have a great optics and laser person with us today. It's John Fredy Barerra Ramirez from University of Antioquia in Medellin, Colombia. So John Fredy is a professor at the Institute of Physics at the University of Antioquia, and serves as coordinator of the Optics and Photonics Group. He's honored with the ICTP Galliano Donardo Award, which is bestowed by ICTP UNESCO and also the International Commission for Optics. He was a future leader in science and technology. And he's been an associate member of the World Academy of Sciences. He's an associate member of ICTP. He's included in the list of 30 scientists under 40 years old that are doing promising research published on the scientific platform LatinAmericaScience.org. He's really done amazing things. He's a senior member of SPIE, a senior member of Optica, and associated with a lot of other organizations. So he's going to be talking about light-based security. And so we've heard about communications, about secure communications, and so the need for better encryption. And so he's going to talk about experimental advances in optical encryption. So these are using optical phenomena instead of algorithms. So at any rate, I'm going to give it to John Fredy. We're going to show his video, and then he's around for questions at the end. So please go ahead.
Hello, everyone, and thank you for being here. My name is John Fredy Barerra Ramirez, and it's a pleasure to present my work on optical encryption. I want to thank the organizer of this event for the kind invitation. Let me share my presentation. I am professor of the Physics Institute of the University of Antioquia in Medellin, Colombia, and also coordinator of the Optical Group. As I said, I'm going to present the work we have done in optical encryption. I'm going to explain what optical encryption is. I'm going to show the most relevant contribution of our group. At the end of the talk, I'm going to present the implementation of a compact optical crypto system. I live in Colombia, in the city of Medellin. This is a picture of part of my city. This is the main campus of my university, and their facilities are near to the main campus. You can see a picture here. Here you can see the Medellin River, part of the metro system here. I am coordinator of the Office of Photonic Groups. We are 6 teachers with some undergraduate and graduate students. This photo was taken recently in the main campus of my university. Encryption systems. Over the years, many encrypted systems that were originally considered secure have eventually been broken. Due to this fact, currently we are working in improve the current system, but also in proposing new encrypted system. And optical processing is a good alternative to this encrypted system because the processing is performed at the speed of light. Optical system provides several degrees of freedom by phase, polarization, or wavelength. And in optical system, we use physical keys instead of digital keys to protect the information. The definition of encryption is quite simple. It's a process of converting information onto unreadable data. Look at here, you have this information. We convert this information into an unreadable data using an encrypted system. The unreadable data is called encrypted image, and this encrypted system contains a key element called security key. The security key allows to encrypt the image, but also recover it when we have all the information of the system. Here, we have the decryption process. The decryption is the reverse process. We are able to recover the original information. We have the encrypted information at the security key. In this case, the system is based in the following fact. If an intruder intercepts the encrypted information, but does not have the security key, the original information cannot be recovered. Therefore, in 1995, it was proposed the first optical crypto system. It's called double random phase encoding in a 4F architecture. The system contains two lenses of focal length f and two random phase masks. One placed in the input plane and the second random phase mask placed in the first Fourier plane. If we insert the object in the input plane and illuminate this input plane, in the output plane, we obtain the encrypted data. Look at here, the encrypted information looks as a noisy pattern due to the use of the random phase mask in the optical system. In this case, the encrypted information is the convolution between the transmittance of the input plane and the Fourier transform of the security key. The Crypto system is also a 4F system. It's a 4F system because the distance between the input and the output plane is 4F, where F is the focal length of the lenses. And if we place the complex conjugated of the encrypted object in the input plane, and the security key in the first Fourier plane, when we illuminate this input plane, in the output plane, we can obtain the recovery. And the key of the execution process is that the random phase changes introduced in the encryption state are compensated using the security key. As we can see, the decryption and encryption system share the same 4F architecture and the security key. That is the element important for decryption. Once we are able to encrypt and decrypt one object, we can handle multiple data in a secure way. Think about this process. We have n objects from O1 to On. We encrypt separately each object using different keys from key 1 to key n, and we obtain the n encrypted objects from E1 to En. If we add together all encrypted objects, we obtain the multiplexing. The multiplexing information contains the information of all encrypted objects in a single data. All the encrypted information is contained in the multiplexing. Then, if you have the multiplexing and the security keys, we are able to recover the original data. Here we can see the multiplexing, the adding of all encrypted objects. The keys are random phase masks, different kind of phase masks. If we have several schemes to record information, we can send the multiplexing and the key 1 to one user, and this user recovers only the object 1. Later on, we can send to the same user the key 2 is able to recover only the object 2. Or we can send the multiplexing to multiple users, and each user receives only one key. The user that receives key 1 recovers object O1 only object O1, and the user that receives multiplexing a key n can recover object On. In this case, we can do two processes with single or multiple users. But we have a limitation. When we try to recover from the multiplexing only one object, we're able to recover the object, like we can see here in the first term, is the recovery of object OL. But the non-recovered objects that represent the second term represent noise over the recovered object. We can see that effect in this image. In figure A, you have one object that was encrypted and decrypted correctly. We are able to recover the object. But we have the multiplexing of 30 encrypted objects. When we try to recover one object, we obtain the object in first term, you can see here in the middle, but the 21 non-recovered objects represent noise over the recovered data. In this case, as the number of multiplexed decrypted objects increase, the noise affecting the recovered data becomes more cynic. Consequence, this noise avoids the recognition of the recovered data. And we have to suppress that noise to protect multiple data using multiplexing techniques. And we found that it's possible to overcome the limitation using modulation. Think about it. We have the encrypted data here, and we have the sinusoidal radio. If we multiply the encrypted data for the sinusoidal radio, we obtain the modulated data, like here. If we apply a Fourier transform over the multiplied data, modulated data, we obtain some diffraction orders. And these diffraction orders contain the information of the encrypted data. The spatial position of these diffraction orders can be controlled choosing the appropriate orientation and pitch of the gradient. We are using this mechanism to apply multiplexing procedures to encrypt multiple data and adding in a single data called multiplexing and recover every data without the effect of the non-recovered data. You can see here an example. We use that idea to encrypt a video. As we know, a video is a sequence of frames projected with certain frequency. Like here, the video is composed by several frames by F1 to Fn. We encrypt separately every frame using a 4F system. Look at here. This is the frame, this is the object, and using the 4F system, we obtain the encrypted frame 1. We are applying the same procedure separately for each of the frames of the video, using the same random phase mask R2, that is the security key. We obtain n encrypted frames, and we modulate each of the encrypted frames using a rating with different orientation and pitch. In this way, you obtain n encrypted and modulated frames. And then we add together all encrypted modulated frames to obtain the multiplexing. In this case, the encrypted video is contained in this multiplexing. Therefore, the encrypted video is a single data called multiplexing. Here, we have all the information encrypted. Then, the recovery of the encrypted video has two steps: a filtering and a decryption process. Filtering, we have the phase conjugated of the multiplexing. We applied a Fourier transform and in the Fourier plane, we obtain the diffraction orders. Each diffraction orders contain the information of one of the encrypted frames. If we apply a filtering process, we are able to select one diffraction order that contains only the information of one of the encrypted frames. And if we apply to each diffraction order a Fourier transform, we are able to recover the complex conjugated of each frame without the noise of the other encrypted frame, other encrypted frames. In this case, modulating the encrypted frames during encryption permits the individual retrieval of each encrypted frame without the superposition from the others, without the noise coming from the others. In the second step is decryption. Once we have the complex conjugated of the encrypted information here, of the encrypted frames, frame from 1 to n, we apply the decryption process with the 4F system, where R2 is the security key, and we recover each frame without the superposition of the other frames. In summary, a moderation processor was introduced during the encryption stage and a filtering process during recovery to enable the retrieval of each frame without the noise produced by the other encrypted frames. In this case, this was the first encrypted video using optical means. Here we can, if we synchronize the filtering and the decrypting procedures, we are able to recover the encrypted video. But if we use a different key from the security key, we recover noise. The video is still encrypted. This contribution was published on Optics Express and was selected for the section Spotlight on Optics from Optical. Once we were able to encrypt and decrypt a video, we extend this grayscale video to encrypt color videos. This paper was also published on Optics Express. Look at here the recording of the video, and we will use a different key from the security key. There are several encrypted systems. One of the most commonly used is the joint transfer correlator encryption system. This system, as you know, as you see here, is more compact than the 4F system because it's a 2F system. Contains a lens of focal length f. In the input plane, you have the object in contact with a random phase mask and the security key. This is also a double random phase encoding technique because we are using two random phase masks. If we illuminate this input plane with a plane wave, in the Fourier plane, the plane key, we obtain the Young power spectrum. And from this Young power spectrum, we are able to obtain the encrypted image. In this case, the encrypted image is the Fourier transform of the object or a random phase mask, and the complex conjugated or the Fourier transform of the security key. Now we are here, we have the encrypted information. As we want to recover the original information, we have to register the information of the security key. This is the next step. To register the information of the security key, we project only the information of the key in the input plane, and we have to introduce two bin splitters, BS1, BS2, and two mirrors, M1 and M2, to obtain a reference bin. In this way, we are able to register in a CCTV camera the information of the Fourier transform of the security key. Here we have the Fourier transform of the security key. Then the decryption system is also a 2F system. We put in the input plane the encrypted image of the Fourier transform of the key, and in the Fourier plane, in the plane K, we are able to recover the original object. We use this system, for example, to encrypt messages of any length. This paper was selected for the IOP select session of IOP Science, and it was selected for introduction in highlights of 2023. And then we use that system to encrypt multiple movies, and each movie with a different key. This system is compact, and we are also using an interferometric system to recording the key. That's important. We face several challenges when we are working with optical processors. For example, here you can see a common images used for simulations and common images used in experimental optical system. It happens because experimental implementation introduces several constraints due to the typical limitation of the optical setups. Therefore, the type of objects that can be effectively processed is restricted. I'm going to show you an example. This kind of image A, is usually used in simulation in virtual optical system. But if we use this image in an experimental optical system, that is joint transfer correlator encrypted system, the correct recovery of the image looks like this. We can recognize some aspect of the image, but the recovery is not equal to the object. We are losing information. In the practice, we have our system is a lens, a system to record the information, a system to project the information of the object, and the QWIN. In this case, the experimental system has a resolution limit imposed by factors such as the physical dimension of the components, the resolution of the projection system, and the pixel size of the camera, and other related constraints. If we want to process the information, the same information, with optical system, experimental system, like in simulation systems, we can do something. Look at here a person, look at the dimension of the elements. One option is change the size of the setup, enlarging the size of the lenses and changing the distances. between the elements is one option. Other option is introduce several elements in the system to perform a more complicated processing. The question is, can the same information used in digital system be processed experimentally without modifying the setup? The question is, I can use this setup to process the same information using an optical virtual system in simulations without changing the size of the elements or the number of elements. It was a challenge because we want to expand the range of possibilities using optical system. And we found the solution using a procedure we call image division. This process consists in divide in equal size sections the object, and each section is projected at the same size as the original object in the system, and we encrypt separately each section and then add together all sections to obtain a multiplexing. This is the example you can see here. This is the object. We use this object in the experimental system. You recover using the right key this object, and then we divide the original object in equal sizes sections, and we project each section with the same size with the original object, and we process each section separately. In this case, we have two sections. Then each encrypted section is multiplexed, and for the multiplexing, we recover the original object. You can see here the result in D when we divide the object in 25 seconds, 25 sections. Okay? Look at here the difference between the case in where the object is projected in B when we have the projection of 25 sections in D. We can see there is an improvement in the recognition of the object after decryption. Then we have another example. This is the original object. The original recovered with the right key without image division, and then we will divide the original object in 9 sections right here and in 25 sections. We can see that the recognition of the object improves according with the number of the sections. Look at here. Then our conclusion is, by applying the division process, the object was successfully processed without requiring any change to the optical setup. We were able to find a way to do it without changing the dimensions of the elements or the number of the elements. At this point, we were able to encrypt from a single letter to a more structured objects, even a video, multiple videos, color images. But if you can see, all the recovered images has noise. And this noise is due to the use of the random phase mask in the optical process. Then, from the practical point of view, the user requires security and high fidelity recovery. We have the security provided for the physical random phase mask and the degrees of freedom of the optical system, but we have noise over the time. We don't have high fidelity recovery. Some researchers try to solve this problem, this noise, to avoid the noise, to reduce or eliminate the noise, but any method allows removing the noise completely. This was a challenge from the beginning of optical encryption in 1995. It was a challenge. A lot of groups around the world were working in this challenge. We were working in that. And we found that the noise problem was not be solved through conventional optical or digital optical techniques. The solution was in the QR code. That now are very popular, but 10 years ago it was different. Look at here. As we know, QR codes are two-dimensional barcodes employed to store information. This system was developed in Japan to drive vehicles during manufacture. They have some advantages, but they are far reading, tolerance to misalignments, and very important is redundancy, allow accurate retrieval of information despite distortions, occlusion, or noise. QR codes can be used freely without the need for alliances. For example, we have here a QR code with a missing portion, but still that missing portion, we are able to read the information contained in the QR code. This is due to the redundancy of the creation of the QR codes. Our idea, also optical encryption and QR coding were created in 1995 and 1994 for different purposes. Our idea was merging optical encryption and QR code. For example, we are here in figure 8. We have the information we want to protect, optical encryption, and instead of encrypt this information, we obtain the corresponding QR code in B. B is the corresponding QR code of the information in A. And instead of encrypting the original information, we encrypt its corresponding QR code. Therefore, in C, we have the encrypted QR code. You can see a noisy pattern. You cannot recognize if there is a encrypted image of a letter, of a video, of a QR code. If we use the decryption procedure with the right key, we obtain the decrypted QR code. Here, we can notice the noise due to the optical processing with the random phase mask. But the advantage is that we read this QR code, for example, with the smartphone, we can recover the original information. Look at here, without the noise. This is the original, and this is the recovered after decryption and reading the QR code. If we apply the conventional procedure with QR codes, we obtain the original information but with noise. In this way, we can see that merging optical encryption and QR coding, we are able to protect information using optical methods, optical processing, experimental system, here, and recovering the information free of noise. This contribution was published in Optical Express and was covered for the section Research Highlights in Nature Photonics with the article Cryptography Quick Response Codes. Also, based on this idea, we have a patent, an invention patent called Optophysical Apparatus and Procedures for Encrypting Information and Recovering Free of Noise. Here, we can see a picture of the optical setup employed for the process. Here, we can see the progression of our research. We are able to encrypt from a single letter, from a more structured object, a QR code, from codes designed specifically for optical encryption and free node recovery, grayscale information here with some advances, color information, structured information, and color and structured information here. We progress from here, and the current results, look at here, this is the decryption of a encrypted real SN. We encrypt a real SN, it's a three-dimensional color XN, but it's real. We take the XN, the real SN, we encrypt the real SN, and then decrypt the real SN. We pass, the evolution was from a single letter to a real 3D color SN. This evolution of our work. In the last years, we were working in a compact encrypted system. As we saw here, we have the optical setup to obtain the encrypted information. It's a single arm setup. But when we want to obtain the information of the security key, we have to add a reference arm. We have a two-arm system. Our idea was obtain a compact system where we can record the encrypted data using the single arm, and with this single arm also recording the encrypted key to avoid the use of a reference. Because when you have a reference arm, you introduce more elements, you need more space, more volume to work. And you increase the requirements of alignment and stability. Our idea was to change this structure for using only a single arm setup. And we achieved this using this idea. Look at here, when you have the optical setup, the single arm setup, when we want to register the encrypted key, we project the object, the key window, we put the contact with a granular diffuser, and we are able to register the young power spectrum and obtain the encrypted key. And for registering the security key, instead of use a reference arm, we put a plain window. We put another window that used to create a plain wave that we can use como the reference wave. In this way, we are replacing a reference wave by a simple window in the input plane. Then we are using a single arm setup for registering the encrypted information at the security key. And this means that there is a significant decrease in the quantity of the elements and the complexity of the crypto system. We achieve this compact system only using a plain wave window. Here we have some experimental results. Based on this system, we found several ways to register the security key. Other way is use a modified Gerber-Saxton algorithm when we record the intensity information of the Fourier transform of the key of the power spectrum between the key and the reference object. We use a reference object, this is a zebra, to retrieve information of the security key. And we use an arbitrary object that was encrypted with the original key to validate the recorded key. The key is recorded thanks to the reference object, but the arbitrary object was encrypted using the original key, and it allows to validate the retrieval key. You can see here in C the decryption using the retrieval key. This is the reference object, and in D we can see the recovery of the arbitrary object using the retrieval key. Here we have simulations, and here we have experimental results. In this way, introducing the idea of reference object, we are able to use a single arm setup to obtain the information of the security key and recover the information of the encrypted objects, as we can see here. Other option to obtain the information of the security key based on a single reference arm is use pictographic key retrieval, in where the key is both in contact with different proofs. Look at here, we have several proofs. There are amplitude-only proofs. We put in contact the key with these proofs and register the output of the crypto system. And with that information, we are able to recover the information, to register the information of the security key. Here, look at here, you have simulation results. This recovery is when we use the conventional JTC crypto system with the reference arm, and this is the information obtained using these proofs. These are the simulation. And as you can see, but another important thing is you can do tailored designs, can be developed to meet specific needs. You can design the element for your needs, for your specific needs, and you don't need to wait to have the money to pay a lot of money for the element and wait they send you the elements. You can do it in your lab in 20 minutes. Here there are some examples. Here, for example, is the prototype. We print so many parts of the prototype using a 3D printer, and we find elements for our research with some design we need for specific purposes. And that are setups developed for teaching. We have undergraduate and graduate students, and we use these elements for teaching. Finally, I want to thank my collaborators from my university, Universidad de Antioquia, some researchers for the Centro de Investigaciones Ópticas, Universidad de La Plata in Argentina. One of my students now is working in Maryland University, and some institutions in my country, some in Argentina, International Center for Theoretical Physics, and the World Academy of Science. Thank you very much for your attention. I welcome to Medellin anytime. Thank you very much.
All right, thank you, John Fredy. So this is actually a low-cost, relatively low-cost experiment in secure communications, and actually an interesting application of optics. I think because there is quite a ecosystem here in optics and laser physics. So this is something that actually is possible to do here, and I think it's very inventive. John Fredy, we actually are running behind time a lot, so we really don't have time for questions, but I can direct anybody here in the audience. Can I give them your email address if they have a question?
Hi, Joe. Hi, everybody. I can give you my email, and if somebody has some question, just let me write me. I am happy to answer any question anytime.
Okay.
There was a missing part of my talk, Joe, was the part of the prototype we developed. This prototype is a very low-cost prototype.
Yeah.
It costs between $1,000 and $1,300 to do basic research. My message, final message is we are able to do independent research using low-cost systems. This is what the part that was missing from my talk because we was so long. I'm sorry, Joe, but this is my message for everybody, for young researchers. And I am happy to answer any question for email.
Okay.
Thank you, Joe, for the invitation and the organizers.
Thank you, John Fredy. And I think it's just a good message that just with a little bit of ingenuity and creativity, you can do a lot for $1,300. Okay. Well, let's thank John Fredy again for a wonderful talk. Thank you.
Thank you.